Okay, so let's talk about some data structures and why some data structures might be better suited for this than others. So first we have the array, and that's most of the time the obvious choice for things because if you need to store a whole bunch of similar pieces of data, it's really easy to just create an array and shove things into it. Now, the reason that we don't really want to use an array for reversing time is because every time we add on a new piece of information, we're taking off the oldest piece. Now, if we wanted to, we could do this in an array. Here we say we have an array and it has 1, 2, 3, 4, 5 pieces of information, 5 elements. And if we were to go ahead and add on a 5th element here, then it's generally pretty easy to do so. And I'm not going to get into the mechanics of how dynamic arrays work. If this array was full, then it would create a new array that was twice the size and put all of these elements into it, which would take 1, 2, 3, 4, 5 operations, right, in the case of an array with 5 elements. But on average, what's called the amortized time, the average time it takes to add an element to an array is constant. It takes the amount of time that it would take to set one of these elements. So adding is not really the problem. The problem comes when we need to get rid of this first one because the first one is all the way up at the front of the array. Now, we could just say, okay, well, we're not going to use that one anymore. We're just going to use the second element and onward. And you could do that, except that every time you're adding on a new frame worth of information, the array is growing and it's going to continue getting longer and longer until you run out of data. So the only alternative to continuously growing your array would be to as soon as you delete whatever's in the first element, then you shift over, you move over the second element over to the first one. So you take all this information and you copy it into the first one, and then you take the information in the third element and you copy it over into the second container spot, and then you take the fourth one and you move that over. So you're shifting over. And essentially you have to hit the entire array. You have to march through the entire array and shift everything over every frame. So in the case of 15 seconds with every frame worth of data, this is going to take a lot of shifting and it's not very efficient. Now, arrays are very good for other things. For example, if at any given point in time we needed to access like the 1001th element, all we would need to do is know which element we want and we could jump right to it. That's called random access. Arrays have random access, and for that reason they're usually pretty desirable to use for most cases, but in this case it's not very efficient to use. So what other containers are there? Well, we have the regular list. Now the list, or sometimes known as the linked list, is a series of items. Generally they're called nodes. So you've got a series of nodes and they're connected by pointers. Essentially you've got two main components to a node, and this is a very simplified version. In reality, lists contain more functionality than this, but say you have a node in a list and it has two main components. The first component is the data. So the data is going to be whatever you're storing in the list. The second component is a pointer, and that pointer points to the next item in the list. It points to the next node. Likewise, that next node has its own data, and it also has a pointer pointing to the next node, which has a pointer pointing to the next node. Now, the last item in the list points to nothing. So it basically has a null pointer. So this is how a list works, and you typically have a special pointer pointing to the head of the list, so that way you can get the very first item if you want to. Now, if you wanted to search this list for a particular item, you can't have random access. You can't just say, give me the 101st or the 102nd item. You would have to march through the list all the way up to that 101st or 102nd item and then retrieve its contents. So it's not very good for random access, but what it is good for is adding and removing things. Because over here in the array, if we wanted to add something to the end, no problem. But if we wanted to add something to the beginning, or say remove something from the beginning, we saw that it would require this shift over of all the elements in the array, which is not very efficient. With a list, no such shift over is necessary. If I wanted to remove the first node, all I would have to do is take this head here and move it over, right? So it's first pointing to this node. I could just take this pointer and point it over here to the second item. And now this item here, this first item, we can go ahead and just delete it. And now our head still points to the beginning of the list, and now we've just gotten rid of that. Now, if we wanted to add a new item to the front of the list, we could easily do so by just simply taking this pointer and having it point to the new item. So even though you can't access any given item instantly, you can instantly add and instantly take away nodes very easily. Now, in an array, if you wanted to add an item inside, in between two elements, or remove an item from the middle of the array, again, you have this shift over issue. But if you wanted to add an item right here in the middle of an array, say right here between these two items, well, it's easy. All you have to do is take this pointer and have it no longer point to this node, just have it come up here and point to this node. And then this node will now point to that node, and it's essentially a very quick and easy process. And the same thing, basically the same principle applies when you are adding, or when you're removing a node. Say we wanted to remove this node, all we would have to do is make this next pointer here for the previous node point to the next node. And then we could simply just cut this one out, and we no longer need to worry about that node. So it's essentially all it involves is updating these next pointers, and then you of course have to manage that memory. You have to make sure that memory is deleted, which if you have Unreal Engine's garbage collection, then whenever no more references point to that, then you know it will be automatically garbage collected. So that's a list. And then a doubly linked list, or sometimes known as just a double linked list, is similar to a list. You have each node which contains data indicated by the pink region here, and then you have two more components. One is a previous pointer, it points to the previous node, and the next is a next pointer, which points to the next node. So each node has two pointers, one pointing forward and one pointing backward. So the very beginning of the list contains a previous pointer, but it's pointing to nothing. So this is going to be a null pointer. Likewise, the very end of the list has a next pointer, and that too is pointing to nothing, so it's also null. Now you have a special type of pointer pointing to the beginning of the list, typically called head, and you have a special pointer pointing to the end of the list, typically called tail. Now, just like with regular linked lists, you can easily add an element in between two nodes. You can easily remove an element from between two nodes. All of that stuff requires constant time to do. It takes the same amount of time to remove the first node as it takes to remove any other node in the list. So why is a doubly linked list good for what we want? Well, what we want to do is be able to add a new node at the end and subtract an old node from from the beginning, and if we always have the head and the tail at our disposal, we can easily do that. So at any given time, we're going to have frames worth of data, right? We're going to have the location, rotation, angular and linear velocity for the object in question. And so we're going to store these in nodes. And because each node has a pointer to the next node and a pointer to the previous node, we have a situation like this. And so every frame, while we're recording data, what we're going to do is we're going to record the data for the current frame, and we're going to stick it here on the end of the list. And then we need to take the oldest piece of data and subtract it. So we can just delete that. And now our new head points to what was the second node in the list. Now it's the first. So we're just going to cycle through these, and essentially it's like we're marching one by one and deleting one node's worth of data each frame and adding a new one. So it's relatively a simple process. Now, how do we use this when we're reversing time? Well, it's pretty simple. All we need to do when we're reversing time is go to the very end of the list, the most recently added node that contains all of the information from that previous frame, and we update the object with that location, rotation, and angular and linear velocities. So on the first frame that we start reversing time, we take this this last node that was added on, we use its data, and then we remove it from the list. The next frame that we're reversing time, we go back one node, and we use its data, and we update the object, and then we remove it from the list. The next frame, we go back in time one frame to this stored data, and we update the object, and we remove it from the list, all the way to the very first frame that we started recording, or at least the beginning of that 15 seconds worth of data, and we use its data, we remove it from the list, and then we say that's it. We've run out of data. That's all of the data we've stored. We're only storing 15 seconds worth of data at any given point in time. Otherwise, if you store too much, you might run out of memory, right? So since we've already reversed time for 15 whole seconds, we've reached the end. That's it. No more effect. And then we have to just stop reversing time at that point. At which point, when we're not reversing time, we can start recording data again. So say we have the right mouse button designated for reversing time. While we're holding that right mouse button down, we're marching backward in our data. Once we reach the end of that 15 seconds of stored data, that's it. We can stop reversing time. And when the right mouse button is not pressed down, we could be recording data. And so we'll go back up to what we were doing before, which was the first frame, store one frame worth of data. The next frame, we store another frame worth of data. The next frame, store another frame worth of data. And once we have 15 seconds worth of data, okay, well now we need to start adding on and then subtracting off of the end, subtracting the oldest node off as we continue. So that's the overall principle of storing data and retrieving data when you're creating a reverse time mechanic such as this. Now, there are some assumptions that we've made when we do this, and one that I said we were making was that, okay, we're assuming that the amount of time that passes by per frame stays constant, and we know that's not the case. We know that as the CPU strain varies, so does the frame rate, and therefore delta time between frames will vary. And so what that means is if you're storing data each frame, and delta time is varying in between frames, well, you might have 10 milliseconds here in between frame 1 and frame 2, and you might have 20 milliseconds in between frame 2 and frame 3. And so as you're reversing time and you're going back, well, time actually never reverses. When your reverse time mechanic is active, time is still running forward. We're just giving the illusion of reversing time. And since time is still running forward, your CPU is causing variations in the frame rate. So as we're going backwards, The real frame rate, the current frame rate, has its own value. So we might go backwards and we might have 8 milliseconds between frames, the first frame as we're going backwards. And then after that frame, we might go 6 milliseconds. And after that frame, we might go 20 milliseconds. And so because the actual frame rate while we're going backwards is different than the delta time between frames back when we saved it, then we're going to have slightly inconsistent results. Now, if the frame rate doesn't vary too much, you're not really going to notice it. But because of the fact that the frame rate is not constant, you have this danger, and we can probably see the effects of this from a very extreme case. So say we're recording data, right? And we have a very fast frame rate, a very short delta time while we're recording. Let's say it's 1 millisecond. I know that's really crazy fast, but for the purposes of this example, just so we can understand, let's say that between frames only 1 millisecond is passing. So we've got a lot of data corresponding to 1 millisecond intervals, and so as an object is flying through the air, right, it might be here 1 frame, and then the next frame, which is only 1 millisecond later, here it is, and then 1 millisecond later, here it is, and 1 millisecond later, here it is, right? And we have a whole bunch of data for a very short amount of time. Now, in reality, since frame rate doesn't stay the same, it can change at any given frame. Let's say now that we're reversing time, right? We've been recording 1 millisecond intervals really, really rapidly, and now we flip the switch, we're going backwards in time, and now suddenly the frame rate changes. Say it goes dramatically higher. Let's say the frame rate goes dramatically lower, the delta time goes dramatically higher. Let's say the time between frames is now 100 milliseconds. So as we're going backwards, this was going forwards in time, that was a 1 millisecond delta time. Now that we're going backwards in time though, we have a very, very long delta time, let's say 100 milliseconds. Okay, I chose this to be a very large disparity between delta times when going forward and going backward. And this is so that we can see the effect of what would happen. So what would happen if we were going backwards, reversing time, and we're going into our data, which corresponds to 1 millisecond intervals. So what would happen? Well, the first frame, that would correspond to the first piece of data, and that wouldn't really be too big of a problem, right? It would be our very last location that we recorded here, so this was where the object was as soon as we flipped the switch and started reversing time, and so it's not really different. Now the next frame, however, while we're reversing time, is 100 milliseconds later. So even though our data corresponds to 4 milliseconds into the past, right, the next piece of data should be 1 millisecond into the past, well, we're not updating it until 100 milliseconds later, which means that right here, where we should be updating is 100 frames worth of data into our data structure. So we should be popping off 100 of these nodes and going back to the 100th item in our list, because that's where the real location should be. So even though we have each millisecond worth of data recorded, well, now that we're going backward, since our frames per second is longer, we're not going to update until way back 100 milliseconds of data in, and so there's a whole bunch of data we don't need. So that's the problem we encounter when we assume that the delta time is going to remain constant. Now, in general, if not too many things are changing from the time we recorded to the time we reverse time, the delta time maybe won't vary that much, but it's a dangerous assumption to make because it's not always going to be true. Now, in the case of the disparity of 1 to 100, right, if we're recording at 1 millisecond and then when we're reversing, delta time is 100 milliseconds, well, what's the perceived effect? What's going to happen is 100 milliseconds into reversing time, we're going to get the very next 1 millisecond location, rotation, and velocities. And we're going to apply that 100 milliseconds later. So when an object was flying maybe quickly through the air, it had a very high velocity. Well, if we're recording very rapidly, and then when we're reversing time, we're updating very slowly, then the object is going to appear to be moving more slowly in reverse. Now, you may say, that's not a bug, it's a feature. If you think it's a really cool effect, oh, that's cool. When it's reversing in slow-mo, no problem. The problem with that, though, is that this feature is not reliable. It changes when the variations in delta time change. And what you want is consistent results, right? So what we're first going to do is we're going to work with the assumption that delta time isn't varying. And then once we get our reverse time mechanic working, then we can address this assumption and create a system that's more robust, that does not depend on delta time not changing. And we're going to do that using linear interpolation. So we'll get to that in a future video once we've already tried this and got something working and we've got time reversing, and once we're ready, we'll start doing some optimizations that take these assumptions into account and no longer depend on those assumptions which may not necessarily be true. So for now, let's go ahead and dive into Unreal Engine. Let's get some code going and let's get our mechanic working, and then later we'll work on those optimizations.